Hi colleagues, how are you today? I hope you're fine. In this series, we will learn about oscillatory motion again. This question was tested in the Physics Olympiad selection. The question is quite simple. You can read this question for 10 seconds. As a visual illustration, watch this animation for a few moments. So, there is a circle with a large diameter. You can imagine this as an empty drum. Inside there is a solid cylinder. It is similar to a coin. When the coin is tipped, it rolls back and forth through the equilibrium point. The coin is in simple harmonic motion, or oscillating at a small angle with a certain angular velocity. So, we are asked to calculate the period of the coin's oscillation. Let's discuss it. The first stage in a physical analysis is identification. We must be able to identify several important quantities that influence the oscillation process. Because the size is larger, we can write the radius of the large cylinder as big R, while the radius of the coin is small r, or just r. The coin is deflected until it reaches this point. The coin then oscillates through the equilibrium point, a point at the bottom of the large cylinder. What can we understand from this process? The coin rotates about two axes. The coin rotates about the center of a large cylinder. The coin rotates about its own axis. Almost similar to the movement of the Earth towards the Sun, isn't it? Thus, on the coin there are two angular displacements. Look at the following animation. This is an animation for a coin slip. This coin will not spin on its own axis. If measured from its original orientation, the angular displacement of the coin is theta. Theta is nothing but the angle formed between the center point of the large cylinder towards the current displacement of the coin and the displacement of the coin at the equilibrium point. This is true, isn't it? Now compare that to the movement of a rolling coin, or a coin that doesn't slip. It turns out that the angular displacement of the coin is greater. Since the coin also rotates about its own axis, there is of course additional angular displacement. The angular displacement is phi. This is what is meant by the coin experiencing two angular displacements. The angular displacement about the large cylinder, theta, and angular displacement about its own axis, phi. We already understand the angular displacement experienced by the coin. Next, what will we do? Of course, we will formulate the angular displacement mathematically. What does the term visually non-slip mean? The coin is said to not slip if the length traveled by each point is the same. So, the length of this arc must be equal to the length of this arc. If this is not the case, then the coin will slip. The length of this arc is big R theta. The length of this arc is r, phi plus theta. So that the coin does not slip, then r, phi plus theta is equal to big R theta. This is a non-slip requirement when viewed from the angular displacement. Now, we will look at the linear speed side. Note the movement of the center of mass of the coin. The center of mass of the coin takes a different path. The displacement of the center of mass of the coin follows this arc, not the arc of the large cylinder. The radius of the path is big R minus R. If you have ever watched a rotational kinematics course, an object is said to not slip if it satisfies the equation V equals big R minus R, omega. Because the rotation radius of the center of mass of the coin is big R minus R. Writing this equation on the answer sheet, you will get a number of points. That you have understood this matter well. In the previous series, we analyzed oscillatory movements through force analysis. This time we will use the concept of mechanical energy. How do we start? That mechanical energy is in quotation marks eternal. The mechanical energy at each point the coin passes has a fixed value. At the equilibrium point, all mechanical energy is in the form of kinetic energy. At the point of maximum displacement, all mechanical energy is in the form of gravitational potential energy. This is true, isn't it? We will start analyzing mechanical energy at the equilibrium point. At this point, the mechanical energy only takes the form of kinetic energy. The rolling coin has two types of kinetic energy: translational kinetic energy and rotational kinetic energy. Let's just write the kinetic energy as follows. We already know the linear velocity of the coin. We here give a different color to omega, because these two omega are different, although both are angular velocities. Angular velocity about the axis itself, and angular velocity about the large cylinder. The angular velocity about its own axis is d dt. The angular velocity about the large cylinder is d theta dt. The moment of inertia of a coin rotating about its own axis is half mr squared. We already know the value of phi before. The derivative of phi with respect to time is big R minus big R over R. We often write time derivatives as dots. Theta dot, theta with a dot on it. We can simplify this equation to look like this. This is the kinetic energy at the equilibrium point. Now, we will analyze the potential energy at maximum displacement. In rotational dynamics courses, we know that potential energy is measured based on changes in the position of an object's center of mass. For a coin, the center of mass is the point in the center of the coin. We will draw a line through this point at the equilibrium point as a reference. Now consider the center of mass of the coin at maximum displacement. The length of this line is big R minus R, cosine theta. Thus, the length of this line is big R minus R, minus the length of it. We can write this length as big R minus R, times 1 minus the cosine of theta. The potential energy of the coin at maximum displacement is mg times big R minus R, times 1 minus the cosine of theta. This is true, isn't it? Well, mechanical energy is the sum of kinetic energy and potential energy. The value of this mechanical energy is conserved. the value of mechanical energy does not change with time. Whatever point the coin is currently in, its mechanical energy is the same. What can we analyze from here? We can differentiate mechanical energy with respect to time. The value of dE dt is 0. Because the value of mechanical energy is constant, not a function of time. However, this is not the case with angular displacement and angular velocity. The amount depends on time. M, big R, and R have fixed values. We can exclude this value from differential notation. The differential of theta dot is 2 theta dot, theta double dot. That value is obtained from the chain rule. I suggest you study the chain rule in differential processes. The differential of 1 minus cosine theta is sine theta, theta dot. These two factors load on theta dot. We can exclude that value. In this equation, theta dot may be 0. Or this factor is equal to 0. We will analyze this factor only. In the question sheet it has been stated that this oscillation takes place for small theta. Numerically, when the value of theta is small, the value of sin theta is the same as the value of theta. This equation can be written as follows. Now we get this form of equation again. If you still remember, there is a second-order differential equation in this form. The two differential equations are identical. Comparing the two equations, omega squared is equal to the square root of 2g over 3 times big R minus r. Of course, the angular velocity value is the root of that value. In rotational kinematics, omega is 2 pi over big T. So, big T is equal to 2 pi root of 3, big R minus r, over 2g. Read the question again more carefully. The radius of the coin is 0.2 big R. This is an easy calculation. Big T is equal to 2 pi root of 6 big R over 5g. This is the period of oscillation of the coin inside the large cylinder. I found a lot of questions related to oscillations for the National Science Olympiad selection. You must understand this concept well. Hope it is useful. And don't forget to watch the next video.